Welcome to this lecture on the growth of functions. In the past 3 lectures, we studied functions and then algorithms. Now, by definition, an algorithm is correct. So once we've established the correctness of an algorithm, typically the thing we are interested in doing next is to analyze the amount of resources that this algorithm requires when it is executed. And the resources we are most interested in are the time it takes to execute and the amount of space or memory that it requires. When we analyze these characteristics of algorithms, we say that we analyze the complexity of the algorithms. Now, in this course, we're only going to focus on time. So, in other words, we're going to analyze the time complexity of algorithms. And in doing so, we are going to connect the two concepts that we previously studied, functions and algorithms. Because what we're going to do is we're going to use functions to analyze the time complexity of algorithms. So, let's think of the time complexity for now as the runtime of the algorithm. Well, the time complexity of the algorithm then depends on the size of the input to the algorithm. So, for example, think of the sorting problem. The runtime of, say, bubble sort will most likely depend on the size of the input, that is, the length of the sequence to be sorted. So, since the time complexity of an algorithm depends on the size of its input, we are going to use a function f of n to represent the time complexity of the runtime, if you wish, of the algorithm. And it's going to be a function of n, which is the size of the input. So this is how functions are connected to algorithms. F of n is a function that represents the time complexity of a given algorithm, where n is the size of the input to the algorithm. First, realize that we only care about the time complexity of an algorithm when the size of its input is really large. So if you're looking at the sorting problem and you're trying to sort a sequence of size 100 or even 1,000 or 100,000 elements, it doesn't matter whether you use bubble sort or insertion sort, because both of these algorithms, or all sorting algorithms, are going to finish very fast, almost instantaneously on today's computers with these kind of inputs. So the time complexity of algorithms really matters when their input is really, really large. So as a result, when we study the growth of functions, in particular the runtime or time complexity function f of n, we're going to focus on its end behavior. That is, what happens at the end of the graph toward the right. In other words, we're going to look at how the function behaves when n gets larger and larger. In other words, when n grows towards positive infinity. So, when you're given an algorithm in this class and in future computer science classes like your algorithms class, you will first have to determine the time complexity of the algorithm. And what that means is you will have to analyze the instructions inside the algorithm and come up with an expression or formula for its runtime f of n. Once you have the function f of n, you will analyze it by comparing it to some well-known so-called reference functions, functions whose end behavior is well understood. So here are a few examples of reference functions. The first one is the logarithmic function we studied earlier. Another one is the linear or the identity function, f of n equals n. If you multiply these two functions, you also get a very well-known reference functions that we haven't seen yet, that we're going to use quite a bit in future lectures. Another reference function is the quadratic function. Another one is the cubic function. And the last one I'm going to mention so far is the exponential function to the base 2. So in this lecture, we're going to study the growth of functions in order to determine the runtime or time complexity of algorithms. And the main tools that we're going to use in this analysis are called the big O notation and the big theta notation. In the next segment, we will start by talking about the big O notation.